Hello and welcome. My name is Nick Brimley, and I am the Marketing Director of the Slag Cement Association. I will be moderating today's webinar, Slag Cement and High Performance Concrete. Our speaker today is Nick Beristain. Nick has worked in numerous positions within Prairie Material for the last 15 years. Throughout his career with Prairie, he has worked as a concrete technician, quality systems specialist, lab manager, quality control manager, and his current role as Senior Manager of Technical Services. He served as the lab supervisor from 2015 to 2018, where he developed mixes for numerous high rises and major infrastructure projects. Along with managing field technical personnel, Nick is responsible for mix designs, research and development, specification review, and all quality systems. If you have any questions during the webinar, we ask all attendees to please use the Q&A feature, and we'll get to your questions at the end. And with that, I will hand it off to you, Nick.
Hi, everyone. Thanks for taking the time to join today. I'm just going to present a short presentation on slag cement, and in particular, the impact and usage it has had in high-performance concrete. Again, I welcome any questions, so please pop those into the Q&A section, and we're happy to tackle those as we go. So with that, I'm going to get started. Just a quick run through of what topics I hope to cover today. Most importantly, what is high performance concrete and some of the common performance requirements that we would see in these types of projects. How slag cement has become a key material in delivering high performance concrete. The production and delivery of HP concrete throughout different regions and limitations. And then finally, a brief discussion on some potential differences you can see in quality control and the testing related to high-performance concrete. So most importantly, as we start out on high-performance concrete, the most common question we receive, whether it be from our customers, whether it be from different agencies, and especially developers of new projects, is what is high-performance concrete? And the answer is that high-performance concrete is most often determined from stakeholders and from owners of projects. We have very specific examples of different agencies identifying specific types of mix designs or criteria for high-performance concrete, but really high performance is in the eye of the beholder. Everything from private commercial, particularly in heavy high-rise construction, as long as heavy highway having a high range of high-performance concrete production. So just a couple projects you can look from, everything from a small pedestrian bridge up to a major high-rise in the city of Chicago is often identified and treated as high-performance concrete. Commonly now, in our business operations, we see high performance utilized in major infrastructure, particularly in bridge construction, but everything from approach slabs all the way through to bridge deck and even pavement is often now identified as high performance concrete, showing that we really have a wide range of applications and market usage for the term high performance. So the main difference that we have seen over the past 10 to 15 years in the development of high performance concrete and its subsequent market is the switch from what was historically known as high strength concrete to long life cycle concrete or high durability concrete. And really, if you take anything away from this presentation, I would say that when you hear the term high performance or the request for high performance, what you should immediately think of is high durability requirements and long life cycles. Historically, we had always been asked with concrete having a relatively long life cycle for 20 to 25, maybe even 30 years. Recent projects have begun asking for 50 years as kind of a baseline, but even 100-year life cycles for communities and infrastructure projects that know that along with financial implications, the demand and the burdens put on different communities when these major infrastructure projects are begun and constructed really should not be asked more than a generation or even a century. And so 100-year life cycle projects are fairly common. We often have 1 to 2 going at any given point in time, really showing how life cycle and those long construction periods are what are now synonymous with high performance concrete. Although high performance concrete has always been very attached to high strength concrete. We often see strengths now that are pretty typical and vanilla, I would say, for any sort of concrete construction. While we usually saw 6,000 to 8,000 to even excesses of 10,000 PSI requirements, what we generally now see for high performance concrete is somewhere in the range of, on the low end, about a 3,500 PSI, but more commonly 4,000 to about 5,000, maybe even touching up to that 6,000 PSI strength requirement. So these are the types of concrete strengths that we would see in normal applications, sidewalks, curb and gutters, nothing that is really aligned with what the market has historically identified as high strength concrete. And so again, this is all just to illustrate for the group how high performance concrete really means different things to each designer, to each owner, and to each different agency that you may interact with on these types of projects. Since high performance concrete is generally considered a relative term, there are many different things that are going to play into what focuses that term for those stakeholders. Some of the common constraints will be locally available materials, what local construction practices are, and then again, for very high specifics, if you have an agency specification that specifies an HP class mix design. This is very common now. We have numerous agencies and organizations that have their own definition of high performance, which in assessment now makes it much easier because you are given a specific list of performance and often placeability requirements to help you really hone in on accurate mix design, and a loss of some of those inefficiencies that you would commonly see with the more relative use of the term high performance. And simply put, the reason for this diversity is twofold. Some of it's a need and some of it's ability. There are often projects that might not specify high strengths, but the life cycle and durability requirements paired with the contractors and materials available to those contractors and suppliers can really help identify what high performance is going to mean in a given market. Some of the performance requirements we typically see attached to high performance, and it's kind of a pick and choose. Some have everything, some have a few, some have some of one and some of the other, are relatively specified. Specifically, you're going to see your common requirements specified in early project documents. So things like life cycle is often going to be specified. Strength almost always is going to be specified. You might start to see some other design concerns, whether that be durability, permeability. Set time is less likely, but also in there. Early strength is often something that we will see to help support normal construction cycles. And along with that, more exotic texts like modulus of elasticity, consistency testing, if we start to get into self-consolidating designs. But then can be some more hidden constructability requirements that are often placed on high performance. Things like workability and retention are thankfully starting to become more common in specification. Things like slump retention, which I'll talk about a little bit later, is often the most common we will see. But overall, the placeability and the finishability, we know with these mixed designs, we're often getting into kind of intricate formwork, more difficult positions, whether or not on an infrastructure or a vertical construction, you're going to have a lot of pumping operations. And so having pumpability and placeability and finishability in those mixed designs is really key, even though it might not be something that people are going to sit there and nitpick over when you're driving 60 miles an hour over something. So all things that need to be considered. But in terms of overall design, the main thing to take away for high performance concrete in that it will often differ from conventional concrete in the sense that we are building durable, long life cycle mixed designs. And for the most part, that is achieved through very aggressive strengthening of the actual concrete paste. So where traditional concrete aggregates often give most of the strength to concrete materials, in this case, the cementitious and the paste binder itself is going to be the strongest portion of the mix design. And so it'll differ in that way. Working through these projects, especially with early discussions before mixes are bid and designed, communication and good specification delivery is always super important. The importance between good communication in all stakeholders, making sure that developers, agencies, IA, testing, everyone is on board, can't really especially for when you're getting into high strength applications, can't help the project enough. Things can fail very quickly if relatively minor things are not discussed. So the sooner you can get everyone together and have a meeting and start to hash out what actual expectations are, the more likely your project is to succeed. Jumping into some of the more constituent-based criteria, like I mentioned earlier, the major portion of high-performance concrete that is going to differ from traditional concrete is often the paste or the binder. Unlike traditional concrete, we have very high-performing, very strong and durable portions of paste. We're trying to minimize a lot of the things related to paste as opposed to some of the other aspects of traditional mix design. So cracking, durability, pumpability, all of those are, for the most part, going to be determined by the characteristics and the material choices we put into the actual concrete paste portion of our mix design. And so with that, we take a very deliberate and measured approach to selecting the types of materials and the quantities of materials we're going to put into these mix designs. Most commonly, what you're going to see in these types of mix designs are a blend of different materials, including essentially all the common SCMs available. The most common we will see, and we'll talk about a little bit more, is slag cement, mostly due to its overwhelming availability and also the beneficial qualities it gives us over the life cycle of the concrete. To a lesser extent, we are now seeing and still continuing to use silica fume and different types of fly ashes, but those have been much more difficult to both secure and control and maintain quality supply lines for. So that has changed over the past few years, leaning more heavily on slag cement overall, as well as, and I don't mention it here, some new, more novel SCMs that are starting to come into the market. As I mentioned earlier, high performance concrete and high strength concrete can always be achieved with numerous different options in terms of specific material choices, and it all is really dependent on the type and requirements of the project. So slag cement tends to shine in a number of different applications. Most importantly, and we use it most commonly to manage thermal concerns. As we get more and more projects that have elements that are designated as mass concrete or with thermal concerns, the use of slag cement just continues to increase in mixed designs. Doing what we can to minimize the real cement content and maximize slag cement content, sometimes in excess of 60 to 70% of the total SCM content. We can do very unique things to deliver a quality but very strong product that has minimal thermal output. So that's really one of the areas where slag cement shines. In terms of other placement concerns and pumpability, managing things through self-consolidating concrete, particularly with high pumping or rebar congestion, can really help with the addition of slag cement to provide stability to the paste matrix. Along with that, the use of fly ash and potentially even silica fume can also help. And finally, achieving long durability, low permeability concrete is usually a blend of all of these materials. Slag cement continues to be the majority of the SCM we consume in designing high performance concrete, but pairing that with a blend of fly ash usage and even a low dose of silica fume can develop an incredibly robust and low permeability concrete that can help eliminate concerns with cracking, shrinkage, and overall penetration into the element itself through the concrete matrix. Before and during the design phase, one of the most important portions of this is evaluating potential supply lines. We do this on both a quality control level and also on a procurement level, ensuring that you're going to have sufficient amounts of material to the best of your ability while going through a project can help. High performance concrete often has heavy pre-workup in terms of laboratory testing and assessment. So if you have to make changes to those material sources midway through the project, it often requires retesting of those materials to verify that performance will meet or exceed recent mix designs. So securing those sufficient supply lines and also testing that the quality will continue to remain is very important, whether that be through documentation such as mill certifications, specific testing such as 618, and then for your aggregates, evaluating for ASR and sulfate resistance, and any sort of mitigation that might be required for actual placement conditions. During the production phase, maintaining the high quality of those supply lines is usually done through assessment of the raw materials. Very common tests that we will see, most everyone knows about, just continuing to maintain gradations and running moistures, which we'll talk a little bit more about, but also on the mortar-based side, performing cubes, performing blane, and then particularly if you're using fly ash, checking for LOI, foam index, and reactivity, so you can accurately adjust your mix design should there be an increase or drop off in performance of any of those raw materials. Aggregate selection continues to be a major portion in helping support the well-designed SCMs. Good, well-graded aggregate can help achieve a lot of the things that we often have to overcompensate with paste for and help alleviate other concerns such as cracking and potential ingress and shrinkage. The key difference that you're also going to see from conventional concrete is smaller aggregates in SCMs or smaller aggregates in high performance mix designs. This is most often an attempt to help provide that well-graded and essentially much more penetrated matrix within the concrete itself. The more different size particles we have, we all know, the better we're going to be in both mixed design consistency, but also in mixed design performance. So trying to do everything we can on an aggregate selection to help eliminate gap grading and especially poorly graded material can really go a long way in reducing shrinkage and reducing durability concerns. Assessing aggregates on an individual basis, some of the things to look for are the overall shape of the aggregate and the face texture of it. In some applications, a rougher texture can be beneficial. In other applications, such as for finishing and for pumping, a rough texture and a poor shape can make a pump work much more. So anything you can do to achieve a cubical shape and find the ideal structure for your mix design and application can really help in the placement and pumpability requirements. Density of the material is also something that we strongly encourage be at least monitored. Most quarries have to provide some level of consistency in the density of the material they provide. However, higher specific gravities are often a good indication of a dense product, which is likely going to provide better overall performance if that is possible. So if you see your densities moving down or shifting greatly, it can play a major impact in the overall volumes you should have in your mix design for aggregate contents. A few, but much less requirement in the sand. The biggest consistency issue we generally see with sand is moisture. However, prior and during mixed design stages, but prior to production, it's often about making sure we're not going to have any sort of reactivity with the sand. ASR testing is very common in most of the regions we operate, so it makes it a bit easier to make those supply decisions early on, but ensuring that we don't have any sort of failures or we're not going to have any reactivity is always a key effort in our initial mix design and supply sourcing issues. When it comes to actual sand performance, we tend to see and use coarser sands. Manufactured sands tend to achieve this result for us and also help benefit with low ASR reactivity. And so we've tried to incorporate more and more manufactured sand into the creation of our high performance mix designs when available to help assuage any sort of ASR designs, or ASR concerns, even though they generally are covered regardless through the higher levels of SCMs utilized for these types of mix designs. One of the downsides of that can be placeability or finishability in certain cases. However, good feedback with aggregate suppliers can always help on that, as they can often make changes both in terms of cleanliness and particle size to help better achieve high pump rates as well as good finish rates. Finus modulus is a great quick hand way to assess that and then also help with mix design on the gradation side during the production and design process. So short changes can be made to help continue to achieve high levels of quality control. Aggregate testing is and continues to be a common standard. Oftentimes, this is specified by agency requirements. Locally in the state of Illinois, we tend to have pretty stringent gradation requirements and testing, both on the side of overall gradations for individual materials, but also on moisture management for those materials. So documenting that and enforcing those types of testing can really help control wild swings in any sort of mixed designs, especially in a lot of cases with high performance mixed designs. Are going to be longer pours over an entire day, consuming large amounts of material. So heading off any sort of swing in moisture or any sort of gradation change can help greatly in terms of consistent production and high quality control. Most often, you're going to see this accomplished through weekly gradations that might actually increase depending on the type of project you're on. So that can always be a helpful check. Along with that, control charts are a great way to help control different outputs on your aggregates and can really help individual technicians make those adjustments collectively and with good guidance. Along with that, monitoring of moisture is the other main production factor that we try to manage. Most plants are set up with live moisture probes, both on mostly on fine aggregate, but we are starting to deploy coarse aggregate moisture probes, and overall our experience with that has been very helpful. And again, helping keep a more consistent blend to the material in terms of aggregates and the moistures that they carry, leading to more consistent concrete production. Admixture selection is going to be highly variable based on individual requirements, whether that's through an agency specification or through customer requirements for constructability. Most commonly, though, you are going to see some of these types of admixtures in almost all of your high performance requirements. I don't think we have any high performance mix designs that do not include high range water reducers. They may not consistently be used at what we would consider the high range dosage, but at a minimum, they're often used at a mid-range dosage to help achieve low water cement ratios and controllable finish on all of our mixed designs, particularly if we're running through pumping placements. Hydration stabilizers and retarding admixtures are also very common, even in the sense of some of the mixed designs that might be optimized for thermal control that have lower outputs and set slower. Hydration stabilizers can be a big help in controlling air contents and controlling slumps over the placement pour. Viscosity modifying actuators are used slightly less, but can often help to reduce some of the more extreme placement issues that can come up, whether that be bleed from the mixed design or potential for segregation if mixed designs are traveling very long pump lines. This can also help reduce friction and within the pump and overall pump pressures, helping for a more consistent and higher yards per hour moving through on job sites. And then finally, we see a fair amount of shrinkage reducing admixture requested or required for these high performance. Again, in a lot of cases, it is to help eliminate or minimize the chance for cracking or ingress points within the concrete itself in the element. And so that is an admixture that we use quite often, but must be used with some care, as shrinkage reducer can have some negative impacts on your overall mix performance if used without much guidance. Some major things to look for during production and delivery of high performance concrete, particularly in the early design portion, but once production starts, identifying the actual requirements to mix design, to make these high performance mix designs. And from that, it's really from a production perspective. So do you have the space within your production facility to ensure you have the right amount of material space, whether that be additional admixture slots on your panel or in your admixture storage? Is it, do you have the sufficient amount of gates and handling for aggregates in order to ensure that you have the bin space and all that? And then finally, and most commonly, do you have the silo space within your production to be able to utilize a sufficient amount of cementitious materials in order to provide those dense, high strength, high performance concrete matrices within your mix design itself? So all of these things are things to consider during the design process. So then once you have a sufficient mix design, you can push that through to the production process and be ready to actually batch in the required amounts. Some of the limitations we often encounter in these sorts of production processes, especially with high performance concrete, is a mechanical limitation. Like I mentioned earlier, do we have adequate material storage systems, whether that be aggregate, cementitious, or admixture tanks and lines? Some become or are lesser known, particularly if you're using siloed silica fume. You need a slightly different setup to make sure you're not having issues moving the silica fume throughout your plant. With more and more safety concerns, we've almost exclusively moved away from bagged or hand-thrown silica fume. So utilizing siloed silica fume is a workup and a process to get set up, but overall makes mix design much easier. The type of plant you're actually going to use for production should be a major concern. It's rare, but we sometimes see specifications that require a certain type of plant for production. However, central mix plants are often the go-to or the preferred method to produce high performance concrete. It's a elimination of potential errors. In our opinion, we have one drum, we have one operator, and we're only asking our delivery drivers to essentially transport the concrete, not mix and eyeball the concrete as a true production method. Do you have and calibrate the use of those moisture probes that we talked about? Controlling your moistures is of the utmost concern, both to maintain the performance requirements, but also to maintain production consistency and keep your customer happy. So having those, making sure they're being utilized, making sure they're being calibrated regularly are all an important part of production before beginning high performance jobs. And then just general consistent maintenance of your equipment, ensuring everything's running, ensuring you're trying to avoid any sort of issues with breakdowns of equipment, having backups in case of a breakdown, all just a good plan to have as a producer before these usually very high profile projects begin. Once projects actually do begin to roll out to production, it's very important and often missed on how many errors can occur during the order taking and dispatching of these projects. So we try to set expectations with customers and with other agencies in terms of the documentation, how documentation will be transmitted, but along with that, what the expectation is to functionally give the customer what they ask for, ensuring that we get the right consistency and the right delivery rate really helps eliminate a lot of quality control issues on site. And so it's always a priority for us. Something that we ask to help establish that is appropriate order window and consistency. If materials are special order or require some sort of advance notice, telling customers that they need to provide 48 hours, 72 hours notice for some of these pours, especially if they're of significant volume, really help us prepare and get our production side ready in case to just provide the best product we can. Another good thing, if you are walking the line between slump and or spread, after an 8-inch slump, the difference between an inch can be pretty dramatic on a job site. So potentially shifting over to a spread designation, because an 8-inch slump can be an 18 to a 21-inch spread. So if a customer has a very good idea of what they want, potentially switching them to that sort of ordering system can really help. One of the other common issues we encounter is minimum loads. We understand oftentimes that people only need a few yards of concrete, but with the high requirements of these types of mix designs, providing a minimum load size can really help eliminate tolerance issues and, again, establish a quality and consistent product. So for us, our minimum load size for any type of high performance and or high strength concrete mix design is 4 cubic yards. It allows the vast majority of our plants a ton of room in terms of actual batching tolerances, and we found it's been very successful moving to that. Helps eliminate some of the other issues during transport and delivery that can occasionally pop up as well. And then finally, just more of a logistic challenge of having appropriate truck staging and achieving proper delivery rates. If we overship or we undership, it causes issues for our customers, which often results in quality issues, either because people are trying to save concrete that is about to time out or to string along concrete as they wait for their next load. So ensuring, again, because these are very often high priority jobs, that we have the right amount of resources available to ship and deliver concrete in a reasonable time frame for the customer, but also being flexible enough to adjust that should we need to either higher demand or lower demand as we see actual performance and placement. And then on more of a local level at an individual plant, working with drivers to ensure that they understand that this is a different type of product, making sure there's no wash water in the drum prior to loading, making sure we standardize wash time and volume. We often do this on a mix by mix basis, as even within high performance concrete, some of the kind of lower strengths might require very less mixing to get to a consistent performance, where some of the higher strength concretes really can have extreme mixing times. We've often seen mixing times for some high performance that require 2 to 3 mix minutes in the plant itself, and then another 5 within the truck, just to ensure the product is consistent and there's no variability in the load itself. To also support that, we generally provide minimum revolutions to the drivers. It's both stamped on their ticket, or now in the case of electronic tickets, displayed on the electronic ticket, so they have quick reference and they're not having to remember each time. And then finally, eliminating water additions wherever possible, both through tracking of any water additions so we can have discussions with contractors after pours, but also, like I talked about, in some of that process water with drivers, making sure their drum is reversed, making sure they're not carrying extra water, making sure they're not washing heavy once they're loading, to help ensure more consistency within these mix designs and achieve the desired performance. Most of this process is actually outlined in C94, doing everything we can to ensure the concrete is properly mixed, especially when you have the addition of multiple cementitious, particularly silica fume, high levels of superplasticizer, other more novel admixtures like we talked about, shrinkage reducing admixture, viscosity modifying admixture, admixtures that are often added at the end of the loading procedure. Ensuring well-mixed concrete can make a world of difference. We try to avoid shrink mixing in any of these events. Occasionally, we do mix uniformity testing just to ensure, knowing we have some high volume pours coming up, that if we need to shrink mix in order to achieve the high volumes requested, that we can do that, but verify that before any sort of changes are made. If you need 90 seconds, 2 minutes, 3 minutes, doing a few test batches can really help work the kinks out of that to make sure that you're going to deliver a consistent product. Reducing batch sizes is something that may occur. If your cementitious or your cement scales can't handle everything, you might actually need to reduce batch sizes. So understanding what actual limitations of production equipment are and communicating that both to your dispatch, logistics, and to customers can help eliminate issues, especially if you need to staff more trucking in order to achieve it because of lower potential output. And then finally, doing everything we can to protect our water cement ratio. Often this is specified and held firm, whether it is a commercial or a private job. So ensuring that there is no water and no phantom water in particular being added without any sort of eyes or visual tracking of it is a priority for these jobs over more conventional concrete applications. And then finally, some of the things you will see and find on actual production and testing. Well, high performance concrete is traditionally cast and managed like everything else. It does tend to put out some rather different characteristics, make cylinders and everything else the same. However, these cylinders tend to be a bit more fickle and a bit more impacted by environmental conditions themselves. In particular, if you get into high levels of SCM replacement, you have to be very cognizant of when you are going to move those cylinders and how they're going to be protected during that initial period, especially for thermal concerns when we have potentially 60 to 70% slag replacement. I always suggest having a conversation if you are going to differ from traditional ASTM specification and potentially leave cylinders to sit longer. That's generally a good idea, especially if that is in a well-controlled environment, just to make sure you are not damaging cylinders that might have lower than conventional concrete early strengths, which is a very real possibility. Some other concerns that these mix designs can have with higher levels of paste content is that they can tend to self-desiccate. So that can create a brittle and non-representative sample through any of the testing aspects. So ensuring that cylinders are protected from the sun, protected from drying, protected from extreme heat changes or extreme loss of heat is a major issue that needs to be overcome and discussed before any sort of project begins. having those conversations with testing labs, with contractors, just really helps up front, so everyone knows that there are very real possibilities to potential negative results if procedures are not followed. As I mentioned a little bit earlier, some of the things that might help really both customers and expectations on the job site in terms of testers is a discussion on what type of consistency people request on site. If traditional slump is acceptable, slump is still a good measure. Again, most of these mix designs have super plasticizer in them in some case. And so you can often achieve higher slumps with this with little to no change. 8-inch, 10-inch even can be achieved while maintaining submitted water cement ratios. And so if that is too rough of a gradation, switching to something like slump, or especially if you are running consolidating mixed designs, can really help dial it in. If you're doing architectural finishes or there's major concerns on rebar congestion, specifying the use for a given pour of a 26-inch spread can really help both the producer, the quality control technician at that yard especially, but then the tester on site and the contractor on site order and receive a product that they actually want to work with. And so figuring out how in the language of ordering consistency can be a huge benefit to all parties involved. As I mentioned as well earlier, these specimens tend to be much more susceptible to abuse on handling and storage conditions. Determining how cylinders are going to be stored, what the expectation is for storage and transport are all very important. Oftentimes something as simple as getting a rack for your specimens during transport can make a world of difference. If the specimens are weaker at that early age strength, bouncing around in the back of a pickup truck is not a good way to demonstrate that your mix design is in fact a good mix design. So again, just having those conversations, especially with testing labs, who can often be a bit more removed from initial stakeholder conversations, can really help eliminate any potential issues, especially if there are issues that might not actually exist in the element itself. Curing conditions are also important. If people get back to traditional curing methods or ponding methods, that can always provide a really good representation of the material itself. Especially a lot of these mix designs might be a little bit more water, might be thirstier for some water during curing. So that can really help. And from what we have found, it much more often aligns to the actual curing methods used on the job site. And so we want to do everything we can to mimic that as best we can. Along with that, pouring in inclement weather, having insulated and storage boxes can really help, whether that be high temperatures or low temperatures. Even a simple cooler, whether or not it has the fancy heating and cooling system, can really just help create a controlled and predictable environment and eliminate a lot of the variation that we often see in concrete specimens. Again, it's very rare that we get onto a concrete mix design that doesn't have a specified strength. So we're always going to see concrete being assessed on compressive strength first and foremost, making sure that, and this might seem pretty straightforward, but has often been an issue, making sure that labs of record and people evaluating the concrete are actually certified to do that sort of testing, especially if you get into concretes with design strengths that are higher than average. It's important to make sure that the lab is certified and conducting the process correctly when they're breaking concrete specimens. Making sure preparation is important, or making sure preparation is followed is also important, particularly for those higher strength specimens, as they're most often supposed to be ground and not capped. And so asking and verifying that that is done correctly is a big part in ensuring that cylinder breaks are reported and assessed as they should be. And then also just equipment requirements. If even though some of these mix designs might not be specified as high strength concrete, the chasing of durability requirements can often necessitate a much stronger concrete design than what might actually be needed. And so making sure that compression machines are suitable to break those types of cylinders is very important. that they can both maintain load rate, document load rate, and also achieve sufficiently high total loads to process these types of specimens and mixed designs. And then finally, you're going to see a whole different smattering of testing as we try to determine what high performance concrete actually is. Again, most of these are going to fall into durability and life cycle assessment. My personal opinion is all of these tests are generally helping achieve some sort of characteristic for the concrete itself. However, it's kind of a grab bag of different tests that don't necessarily accurately represent performance in the field, but like most of the other tests we see, do our best to present a reasonable facsimile of what we think it was going to experience in the field. And so the most common durability assessments that we are going to see, and I'll provide a bit more background here in a second. Restrained ring shrinkage is a very common run. We see a bit more of a real world shrinkage test as opposed to linear shrinkage. Rapid chloride permeability and surface resistivity kind of make up the bulk of durability and life cycle assessment, very commonly done on most high performance mix requirements that we see. And then there's also often a request for general petrographic assessment. This is going to provide kind of a different look at the concrete and essentially verify that it is what the mix designer says it is. Along with that, though, we have seen a pretty common kind of accompaniment of tests of mixed testing that can also help. It usually helps again with durability, but there's also some constructability support that we'll tend to gather for that. So hardened air is a very common one. We know well proportioned and well-distributed air systems are going to provide better durability in freeze-thaw environments than just about anything else. Often having aggregates ASR tested, both in terms of aggregates themselves and as a whole. And so whether or not they're going to be able to mitigate any potential ASR reactivity is a normal assessment. Slump retention is a great test. It's usually pretty straightforward. Continuing to mix the concrete either in a mixing transport vehicle or in a lab mixer, just to ensure there will not be any flash sets or rapid loss of slump, is a great way to provide confidence both to the producer and to the contractor that there will be no such issues on site. And then more recently, the adoption of maturity curves continues to grow and grow. This is also helpful because it does eliminate some of the unknown in these types of mix designs, so people know what to expect, how the concrete mix design should perform as it functionally has been assessed over a long life cycle already. It also helps greatly with some of the inconsistencies often provided by concrete cylinder casting. So this is a quick view of a modulus of elasticity test. It's personally one of the more boring tests that you can actually conduct as a concrete producer, as you are looking to see deformation, both elastic and inelastic, but primarily just measuring the microscopic change in height of the cylinder, but also the microscopic potential expansion at the center of the cylinder, and how well it snaps back from that deformation. So if anyone ever asks you to witness a modulus of elasticity test, you're going to watch the cylinder for 15 minutes and then walk away not seeing anything. So save yourself the 15 minutes and say no, thank you. Life cycle testing, like I said, this is kind of the heart and soul of high performance concrete, both in terms of resistivity and also overall chloride penetration. These are the tests you're most commonly going to see. A lot of producers are actually starting to bring this into their own labs now just to do assessments prior to actual mix construction, so they know where they have to put their mix designs at and what is actually performing well. But these will be the most common tests you're likely to see with the specification of high performance concrete. The restrained ring shrinkage test, it comes in many different flavors, but in all cases, you are going to cast a large ring of concrete and then see how long it takes for it to crack if it does crack. Again, this helps with the durability testing in knowing what sort of exposure there is to potential ingress methods in the form of cracks. You can have them covered, you can have them partially covered, top, bottom, sides. There's a whole bunch of different variations of that. So make sure you check your spec as to what you need to do and how it needs to be covered if you are forced to run a restrained ring shrinkage test. And then finally, the good old standby freeze-thaw durability C666, potentially one of the most aggressive concrete tests out there. This is required less and less in our experience and what I've especially seen lately, but it is still out there and people do still ask for it. It is a very aggressive test, as I mentioned, but it is a good measure overall of whether or not your concrete is going to be able to stand up over especially those 50 and 100-year life cycles that are now being requested for high performance concrete. And with that, that is the end of my presentation. I'm glad everyone got to join, and if anyone has any questions now, I'm happy to jump in and talk through those.
Thank you, Nick. We have a couple questions here. And please, everyone, please feel free to use the Q&A section here if you have any other questions you'd like to ask. But our first one, you touched upon the 100-year life cycles, the expectations for some of those projects. Do you see that being a continuous trend? Do you see more projects? Is there an expectation for them to at that point?
I don't think there is. I wouldn't say that there is an expectation at this point, but I will say that I assume that is going to start to normalize. And the reason being, besides the burden that puts on builders and developers, and especially government agencies and government funding bodies, they don't want to burden their constituents with consistent construction, even though I think we all live in a world of consistent construction. But I think as recent guidelines, particularly from the sustainability functions, come down, that is going to kind of, in a different way, push forth long life cycle projects. And now it's being managed on more of a CO2 output or emissions based, but really what is going to help concrete as a building material is showing that it can achieve those life cycles, helping draw down some of the carbon emissions on a per unit basis.
Perfect. And the other question we have here, so it's a little more open-ended. What are some primary challenges or expectations you're seeing with the production of high-performance concrete that maybe you haven't seen in the years past?
I think some of the most common challenges we see is often a bit of a disconnect between specifiers or designers and often in-place construction methods. And so asking for instance, we had a job recently that required high-performance concrete in the form of very high mass concrete thermal control concerns that also requested 2-day strengths. And so we see a pretty big disconnect between what people are asking in terms of practical application and what can actually be constructed. And I think in a lot of cases, that is the result of just disconnects between concrete contractors in particular and the engineers and specifiers who are requesting certain jobs. So people see a spec, it looks nice and shiny to them, they include certain specs in, and oftentimes those specs just don't align with real world application and construction requirements.
Excellent. Looks like we got a couple more questions here. The first one is, considering the high performance mainly at early ages and low reactivity of slag cement, what is the route to achieve high performance concrete using slag?
I would say in most cases, it kind of, as a segue from my last question, or the last question, we've seen some industry acknowledgement that is going to be the case. There might be lower age strengths. And the industry is kind of capitalized on that, assuming that there will be longer overall life cycle gain. And so they've tried to be as flexible as they can with that, either specifying potentially a lower early age acceptance strengths or even construction strengths so they can move equipment or whatever they need to do. The Illinois Tollway in particular has been very good about that facet. But where we need to provide some earlier strengths, there are other options. If silica fume is a viable option, that's always a great thing, because even with some of the thermal concerns, usually a small dose of silica fume can really juice early strengths just in the overall particle size, so not even in the reactivity portion of it. But driving down through lower water cement ratios is another option. And then again, providing good aggregate blends can really help overcome some of the lower early age strengths that we've seen. And then finally, and this is much newer, strength enhancing admixtures can really be utilized in this particular area to help offset some of those losses. So that's something we're actively exploring right now. We've used it on a few jobs, but in many cases, we know ultimate strength might not really be an issue for strength enhancers, but helping us at those early age strengths counteract some of the downsides of using more SCMs has really been beneficial.
Awesome. And then the last question we have here is, what other types of tests do you see that could be valuable for specifying or determining performance of projects using HP cement?
Oh, that's a good one. So in my opinion, and I did hit on this, maturity testing is a great one. Anything we can do to mimic and mock whatever sort of actual in place construction performance is something we want to move to. Utilizing cylinders is still a good back check or a second option for that, but a maturity curve helps us understand if the concrete much earlier than 28 or even 7 days is doing what we think it's going to do, if it's following that maturity curve. So I really am a strong proponent of pushing maturity when we can. Along with that, I would say kind of in a similar vein to maturity, but thermal profile for concrete, whether that be adiabatic calorimetry or some of the other different types of calorimetry, can really be helpful, because then we can both test and understand on much smaller quantities of concrete what we think some of the performance characteristics are going to be and how we can adjust. So that's something that can be very useful and also helpful if you have to model for thermal concerns. Other than that, there are a lot of exciting tests out there. I think there's been kind of a lockstep of new tests coming out with some of the new materials that have been coming out, whether that be changes to our cements in the form of blended cements or some of the more novel cements that are coming out, and like the zero carbon or the truly like non-Portland based cements. But then along with that too, some of the different SCMs and that sort of stuff, we've seen some, I think the testing market is trying to, or the testing field is trying to kind of catch up with that. So for me, I think those do a good job of assessing that and trying to put that through on a long life cycle. I'll think about that one some more though and try to get more information, because that's a very good question. I was not prepared for that one.
Perfect. Well, I want to once again thank you here for presenting today. All of you for attending this webinar as well. If you have any more questions at a later time, please feel free to email us at info@slagcement.org, and we'll get to those questions. Also, this webinar will be available on demand on SCA's website and YouTube channel, so keep an eye out for that as well. Thank you, Nick, for presenting, and thank all of you for being here.
Thanks, everyone. Hope you enjoyed it.